As the 19th century approached its end, the world of science stood upon a towering mountain of achievement. The laws of Newton, the theories of Maxwell, and the principles of thermodynamics had built what many believed was a complete and unshakable description of the universe. Every movement of the stars, every beam of light, every wave of sound seemed to fit perfectly into the grand framework of classical physics. For the first time in human history, it appeared that nature had been conquered through reason. Physicists believed that, in essence, everything had been discovered. All that remained were a few minor details to be polished. Yet, beneath this confidence, there was a quiet riddle, a subtle inconsistency that refused to be solved. It emerged from one of the most ordinary, yet mysterious phenomena in all of nature: the way objects emit light when they are heated. Imagine a piece of iron placed into a roaring furnace. At first it glows faintly red, then orange, and eventually turns white hot as its temperature rises. This behavior, known as Blackbody radiation, fascinated scientists for decades. The term Blackbody refers to an idealized object that absorbs all radiation falling upon it and emits energy perfectly according to its temperature. It is a concept that allowed scientists to study pure radiation, stripped of any complicating factors. In the late 1800s, physicists were trying to find a mathematical law that could describe exactly how this radiation changed with temperature, how the intensity of light varied across different colors or wavelengths. The goal was simple: to find a universal law that could describe the glow of everything from a hot metal to the sun itself. Experiments were conducted with increasing precision. Instruments measured how much radiation was emitted at each wavelength for a given temperature. When plotted on a graph, the results formed a distinct curve. The radiation rose to a peak at a certain wavelength, then dropped off on either side. At low temperatures, the peak was in the red region of the spectrum. As the temperature increased, the peak shifted toward blue. It was a smooth, beautiful pattern, yet when the leading theories of classical physics tried to describe it, they failed spectacularly. According to classical electrodynamics, light and radiation were waves that could have any frequency. Physicists believed that energy could be distributed continuously among all these frequencies. When Lord Rayleigh and Sir James Jeans applied this principle, they derived a formula predicting that at short wavelengths, or high frequencies, the emitted energy should become infinitely large. This was absurd. If that were true, every hot object in the universe would instantly radiate infinite energy and vanish in a blinding flash of ultraviolet light. But that never happened. The experimental data showed that radiation at high frequencies actually dropped sharply to zero. The failure of classical theory in this region became known as the ultraviolet catastrophe. This catastrophe was more than a mathematical inconvenience. It was a crisis for physics itself. The pillars of classical theory, thermodynamics, electromagnetism, and mechanics, could not all be correct if they led to such contradictions. Physicists were unsettled. Some dismissed the anomaly as a temporary problem, hoping that a clever adjustment to existing equations would fix it. Others suspected that a deeper flaw lurked within the very foundations of classical physics. Yet few were willing to abandon the belief that nature was continuous, that energy, like time and space, flowed in an unbroken stream. It was into this intellectual storm that a quiet, disciplined German physicist named Max Planck stepped forward. Planck was not a revolutionary by nature. He was a man of logic, order, and precision. Born in 1858 in Kiel, Germany, Planck had always been drawn to the harmony of mathematics and the beauty of nature's laws. To him, physics was not just a profession, but a pursuit of truth, a way to understand the underlying order of the universe. He had spent much of his career working on thermodynamics, particularly the second law, which deals with entropy and the direction of natural processes. When Planck turned his attention to the problem of blackbody radiation, he saw it not as a rebellion against classical physics, but as an opportunity to extend its power. At the Berlin Physical Institute, Planck began his work by carefully studying the existing data on blackbody radiation, especially the results obtained by Heinrich Rubens and Ferdinand Kerlbaum, who had made highly accurate measurements of the radiation spectrum. Planck was determined to find a mathematical formula that could fit these observations precisely. Day after day, he adjusted equations, plotted curves, and tested different assumptions. For months, the results refused to cooperate. Classical theory worked well at long wavelengths but broke down entirely at short ones. The numbers simply refused to match. In a moment of creative desperation, Planck decided to take a new approach. He treated the exchange of energy between matter and radiation not as a smooth, continuous process, but as something that happened in discrete steps. This was a radical idea, almost unthinkable at the time. It was as if energy came in tiny packets rather than a continuous flow. Planck imagined that the oscillators within the walls of a heated body could emit or absorb energy only in specific amounts, proportional to the frequency of radiation. In mathematical form, he expressed this relationship as etom, where E is energy, null is frequency, and h is a new constant of proportionality, what we now call Planck's constant. To Planck, this was initially just a clever trick, a mathematical device to make the equations fit. He did not fully realize the profound implications of what he had written. But when he inserted this quantized assumption into his formulas, something miraculous happened. The theoretical curve matched the experimental data perfectly. The radiation intensity rose to a peak and then declined smoothly at higher frequencies, just as observed in nature. The ultraviolet catastrophe vanished. In that moment, Planck knew he had uncovered something extraordinary. Yet even then, he hesitated to believe it fully. The notion that energy was quantized contradicted centuries of scientific thinking. Classical physics assumed that all measurable quantities, energy, momentum, position, varied continuously. The idea that nature could jump from one value to another in discrete steps seemed almost mystical. Planck himself later described the realization as an act of desperation. He did not claim to understand why energy should behave this way, he only knew that it did. His formula, published in 1900, marked a turning point in the history of science. Although it appeared modest at first, it contained within it the seeds of a revolution that would ultimately reshape all of physics. For the first time, scientists had to accept that the laws governing the microscopic world might be fundamentally different from those of the macroscopic one. The early reaction to Planck's work was cautious. Many physicists regarded his theory as a mathematical curiosity, a temporary fix that would eventually be replaced by a more classical explanation. Even Planck himself did not initially see it as the birth of a new science. But the precision of his formula could not be denied. As new experimental data confirmed his predictions again and again, curiosity turned into serious attention. In the years that followed, Planck's idea began to attract some of the brightest minds in physics. Among them was a young patent clerk named Albert Einstein. Einstein recognized the true depth of Planck's insight and took it a step further. In 1905, he proposed that light itself was made of these energy quanta, later called photons. This bold suggestion helped explain the photoelectric effect, where light could knock electrons off metal surfaces. What had begun as a mathematical adjustment by Planck had now evolved into a new view of light and matter. But before the world could reach that point, the significance of Planck's initial struggle needed to be understood. His journey began with failure, the failure of classical physics to explain one of nature's simplest phenomena. This failure was not a sign of weakness but a gateway to discovery. Every failed equation, every contradiction, every puzzling graph pushed Planck closer to a realization that would redefine science itself. The Blackbody problem forced scientists to confront the limitations of their own assumptions. They learned that the continuous world of classical mechanics, which worked beautifully for planets and pendulums, could not describe the invisible realm of atoms and light. Energy did not behave like water flowing through a stream, it behaved like a ladder. jumping from one rung to another. This was a shocking idea, one that would eventually give rise to the quantum revolution. As Planck refined his theory, he also sought a deeper understanding of why quantization worked. He delved into statistical mechanics, exploring the relationship between entropy and energy. By combining Boltzmann's ideas of probability with his own quantized assumption, he found that the laws of thermodynamics could be extended to describe radiation. This synthesis was elegant and profound. It revealed that the microscopic world was governed by discrete patterns of probability rather than smooth curves of certainty. The concept of the blackbody was more than a scientific curiosity. It was a window into the fundamental structure of reality. Every glowing ember, every shining star, every warm object emitted radiation that followed Planck's law. It was a universal principle, one that applied to the entire cosmos. The same formula that described the dull red glow of an iron furnace also described the brilliant light of distant galaxies. Planck's perseverance, born out of frustration with classical theory, had uncovered a hidden order within the chaos of energy. He had shown that the universe operated not through the smooth elegance of continuous motion, but through the rhythmic pulse of quantized energy. Tiny, indivisible units that danced at the foundation of existence. For centuries, scientists had believed that nature could be understood completely through continuity and determinism. But Planck's discovery shattered that illusion. The very idea that energy came in discrete packets suggested that nature itself was built on uncertainty, that the smallest scales of reality were not predictable with perfect precision. This was the beginning of a new age, an age where probability replaced certainty and imagination became as essential as calculation. Planck's struggle with the blackbody problem symbolized the transition between two worlds, the classical and the quantum. His success did not come from rejecting the old theories outright, but from daring to go beyond their boundaries. He was not searching for a revolution, he was seeking understanding. Yet in doing so, he initiated one of the greatest revolutions in human thought. The failure of classical physics to explain blackbody radiation was not just a scientific problem, it was a philosophical awakening. It reminded humanity that even the most powerful ideas could reach their limits, and that progress often begins where certainty ends. The elegant equations of Newton and Maxwell had described a universe of predictable motion. But Planck revealed a universe of hidden patterns, a universe that behaved in mysterious, discontinuous ways. As the 20th century dawned, the old world of physics began to fade. In its place emerged a new vision of reality, one built upon the foundation that Planck had laid. His theory of quanta was the first crack in the wall of classical certainty, and through that crack poured the light of a new understanding. The journey that began with a simple question about the color of heated metal had led to a profound truth about the nature of existence. Max Planck's realization that classical physics could not explain blackbody radiation was more than a triumph of mathematics. It was a testament to the power of curiosity and persistence. It showed that when the known world fails to make sense, the unknown world waits patiently to be discovered. The dawn of the 20th century shimmered with both promise and confusion. Planck's strange equation had fit the data perfectly, but few truly grasped what it meant. In laboratories and universities across Europe, whispers spread that something fundamental had shifted. The proud architecture of classical physics, so orderly, so predictable, now showed cracks running through its foundation. Yet even as Planck's formula solved the riddle of blackbody radiation, the meaning of those discrete energy packets remained elusive. What exactly were these quanta? Were they real fragments of energy or merely a convenient mathematical trick? Planck himself was torn between conviction and disbelief. He often described his own feelings as reluctant wonder. He had always considered himself a conservative thinker, loyal to the continuity and determinism that defined 19th century science. To him, the universe was a grand symphony of cause and effect, governed by laws that left no room for randomness. But his new law of radiation whispered of discontinuity, a rhythm of sudden jumps rather than a smooth melody. In his diary, Planck admitted that he had been forced to take this desperate step, not because he wished to, but because no other path matched the experimental truth. The beauty of Planck's law lay in its simplicity and precision. Using his constant, h, he created a bridge between the microscopic world of atoms and the macroscopic world of heat and light. When graphed, his curve fit every measurement, from the deep red glow of warm iron to the blue brilliance of stars. Scientists who had wrestled for decades with the Blackbody problem could not ignore it. The ultraviolet catastrophe had disappeared, replaced by a graceful curve that mirrored reality itself. For the first time, physics could explain why the night sky glowed as it did, why the sun's spectrum took its particular shape, and why the world around us radiated warmth instead of infinity. Still, the philosophical implications unsettled many. The idea that energy could exist only in discrete quanta suggested a universe that was grainy at its core. It was as if reality itself were built from indivisible bits of action, tiny bricks from which everything else emerged. To the classical physicist, this was almost heresy. For centuries, science had been guided by the dream of smoothness, of continuous laws that described everything from tides to starlight. Planck's constant shattered that dream, introducing the notion that nature might make leaps. The early years of the 20th century became a period of hesitation. Physicists admired Planck's success, but avoided its implications. They continued to use his law because it worked, while secretly hoping that someone would find a way to explain it within the old framework. Yet the more they studied radiation, the clearer it became that continuity could no longer describe reality. In 1905, when Albert Einstein proposed that light itself consisted of individual quanta, later called photons, the revolutionary meaning of Planck's discovery began to crystallize. Einstein's interpretation went beyond Planck's cautious mathematics. He declared that these packets of energy were not mere abstractions but actual particles of light. They carried momentum, collided with matter, and could eject electrons from metal surfaces in the photoelectric effect. This simple explanation not only proved correct but also confirmed that the quantum world was real. Planck, though uneasy, recognized the brilliance of Einstein's insight. It meant that his act of desperation had revealed a deep truth about the universe, that energy exchange occurred in finite steps. As this idea spread, physics began to transform from the inside out. Young scientists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger took inspiration from Planck's quanta and applied them to atoms themselves. They discovered that electrons could orbit a nucleus only at certain energy levels, jumping from one to another in bursts that matched Planck's law. The atom, once imagined as a miniature solar system governed by continuous motion, became a pulsating structure of quantized transitions. Every photon emitted by an atom was a messenger from Planck's constant, a signature of discrete energy at work. The failure of classical physics to explain blackbody radiation thus became the birthplace of a new worldview. The smooth predictability of Newton's clockwork universe gave way to the shimmering uncertainty of quantum mechanics. Determinism yielded to probability, and the very language of science began to change. Where classical physics spoke of certainty, quantum theory spoke of chance. Where classical laws predicted exact outcomes, quantum equations offered only likelihoods. It was an intellectual earthquake whose tremors are still felt today. Yet amid this revolution, it is essential to remember the quiet persistence that made it possible. Planck did not set out to destroy classical physics. He sought clarity in the face of contradiction. He respected the past but refused to ignore evidence. His success was born from patience, meticulous calculation, and an unwavering belief that nature, however mysterious, could be understood. Even when his discovery threatened to overturn everything he held true, he stood by the numbers. Science, after all, is loyalty to truth above tradition. The significance of Planck's achievement extended beyond physics. It altered humanity's conception of reality. The idea that energy could not be infinitely divided suggested limits to measurement and perception. Nature was no longer infinitely smooth, it was pixelated, quantized, woven from finite strands of existence. Every beam of light, every vibration of heat, every interaction of matter carried within it the stamp of H, Planck's constant. It was as if the universe had revealed its smallest heartbeat. Over time, the constant found its way into every corner of modern science. It appeared in equations describing atomic spectra, chemical reactions, and even the structure of space and time. Planck's once obscure symbol became one of the fundamental constants of nature, standing beside the speed of light and the gravitational constant. It defined the scale of the microscopic world, the realm where quantum effects dominate and classical intuition fails. Without it, we could not design lasers, semiconductors, or quantum computers. Every advance in modern technology owes a silent debt to that moment in 1900 when Planck chose to defy convention. But perhaps the most profound legacy of Planck's struggle is philosophical. His work forced scientists to confront the limits of human knowledge. The universe, once imagined as fully knowable through deterministic laws, revealed an irreducible element of mystery. No longer could physicists claim that, given enough information, they could predict every event in the cosmos. The quantum world introduced randomness at the heart of creation. To some, this was unsettling; to others, it was liberating. It meant that nature was not a static machine, but a dynamic tapestry of probabilities, a universe alive with possibility. Looking back, it is remarkable to see how the failure of classical physics became the seed of progress. What began as a simple discrepancy in experimental data grew into a revolution that redefined reality. Planck's willingness to question the unquestionable transformed a crisis into creation. The ultraviolet catastrophe, once a symbol of failure, became the threshold of modern physics. Out of that apparent chaos emerged a new harmony, one deeper, stranger, and more beautiful than anyone had imagined. In the decades that followed, the quantum principle expanded into every realm of science. Bohr's model of the atom, Heisenberg's uncertainty, Schrödinger's wave mechanics, all traced their lineage to Planck's constant. Even Einstein, though he later resisted the probabilistic nature of quantum theory, built his earliest triumphs upon Planck's insight. The 20th century became the century of the quantum, and its light illuminated everything from nuclear energy to the structure of DNA. Planck lived long enough to witness the triumph of his reluctant discovery. He watched as a new generation of physicists embraced the quantum world with enthusiasm and imagination. Though he remained cautious, he took quiet pride in knowing that his elementary quanta had become the cornerstone of modern thought. In 1918, he received the Nobel Prize in Physics for his discovery of energy quanta, a recognition not only of a formula, but of a new vision of nature. Beyond the awards and honors, Planck's true reward lay in understanding. He had shown that progress in science often comes from confronting failure, not avoiding it. The Blackbody problem had seemed a minor inconsistency, yet it forced humanity to rewrite its understanding of reality. It revealed that beneath the calm surface of nature lay a restless ocean of quanta, flickering in and out of existence, shaping every spark of light and every whisper of energy. In retrospect, the failure of classical physics to explain blackbody radiation was a gift. It reminded scientists that even the most successful theories can stumble, and that those stumbles may point the way to deeper truths. Planck's discovery was not born from rebellion, but from respect, from a careful attention to detail and an unwillingness to ignore contradiction. His humility before nature allowed him to see what others had missed. Today, every student who learns about quantum mechanics begins with Planck's constant. It is the gateway to understanding the microscopic universe. From the glow of a light bulb to the radiation left over from the Big Bang, Planck's law continues to describe the patterns of energy that fill the cosmos. The equation he once considered a desperate guess has become one of the most precise and powerful tools in science. As the story comes full circle, we see that the failure of classical physics was not an ending, but a beginning. It was the moment when humanity took its first step into the quantum realm, guided by a man who sought truth above certainty. The world he revealed is stranger than anyone could have imagined, where particles behave like waves, where emptiness teems with energy, and where reality unfolds in quanta of action. Yet it is also a world of profound beauty, where even the smallest constant connects the infinite with the infinitesimal. The legacy of Max Planck is not merely a theory but a lesson. It teaches that discovery often hides within contradiction, that progress arises from doubt, and that the universe rewards those who listen to its faintest whispers. The Blackbody problem, once an embarrassment to physics, became the key to unlocking the quantum age. Through Planck's perseverance, the failure of classical physics transformed into the triumph of human understanding. And so, as we look back on that turning point more than a century later, we can trace every photon, every atom, every quantum leap to the moment when one man dared to question the continuous and imagine the discrete. In that act, science was reborn. The universe, once thought to be smooth and predictable, revealed itself as a symphony of quanta, a music that began with Planck's desperate equation and still resonates through every discovery that followed. At the turn of the 20th century, a quiet revolution was forming in the mind of a single physicist. Max Planck, a man of calm intellect and disciplined reason, had stumbled upon a problem so simple in appearance, yet so profound in consequence that it would shake the very foundations of science. He was studying how heat and light were related, a problem that had frustrated physicists for decades. The goal was to understand how energy was radiated from heated bodies, and yet the answers offered by classical physics simply refused to match the evidence of the real world. Planck had already solved the mathematical form of the radiation curve, but his formula was different, strange. To make it fit the experimental data, he had introduced a constant that limited how energy could be exchanged between matter and radiation. What emerged from his equations was an idea both elegant and unsettling: energy, the continuous essence of nature, could not flow freely in any amount. It came only in small, fixed bundles, discrete packets that could not be divided further. These packets were what he called quanta. In that moment, Planck unknowingly crossed a boundary that separated two worlds: the familiar, continuous world of classical physics and a new, fragmented realm of the microscopic. The word quantum, derived from the Latin quantus, meaning how much, represented a concept that defied everything physicists had believed for centuries. For generations, scientists had assumed that all quantities in nature could vary smoothly, just as one could pour water into a cup by any fraction. It was assumed that energy, too, could be emitted or absorbed in infinitely divisible portions. But Planck's equations told a different story. Nature, it seemed, did not pour energy, it handed it out in separate coins. Planck's constant, h, became the size of those coins, the smallest unit of energy possible for a given frequency of radiation. The relationship he discovered, eta, was shockingly simple. The energy of each quantum was directly proportional to the frequency of light. Higher frequency meant higher energy, lower frequency, less. This was more than just a formula, it was a new law of nature. For the first time, the universe revealed that its transactions of energy occurred not as a smooth flow, but as a rhythm of steps, each determined by h. To understand what this truly meant, imagine a violin string. In classical physics, one might think the string could vibrate at any frequency whatsoever, producing an infinite range of tones. But Planck's insight implied that nature only allowed certain specific notes, that between these notes silence reigned. Light, heat, and every form of radiation were no longer continuous symphonies, but melodies composed of distinct beats. The implications were enormous. By proposing energy quantization, Planck had introduced discreteness into the heart of physics, something that went against the grain of every established theory. Even Planck himself struggled to accept it. He considered the assumption a temporary bridge, a mathematical trick to fix an unsolved problem, not the revelation of a new reality. Yet mathematics, as always, refused to lie. The experimental results fit perfectly, leaving no escape from the truth his equation implied. Planck's mind wrestled with the meaning of his own creation. He was not a man of reckless speculation but of cautious reasoning. He admired Newton, worshipped Maxwell, and respected the elegant continuity of classical physics. But now, his own work suggested that the energy exchange between atoms and radiation occurred in sudden leaps, not gradual transitions. Every time a molecule absorbed or emitted light, it did so in chunks, one quantum at a time. Between these leaps, there was nothing, no intermediate stage, no smooth transition. This idea was not merely counterintuitive, it was almost heretical. And yet it explained everything: the mysterious behavior of blackbody radiation, the failure of previous formulas, the way heat transformed into light. All became clear through the lens of quantization. The intensity of radiation at each wavelength could now be calculated with astonishing accuracy. The experimental curves that had once mocked classical theory now bowed perfectly to Planck's formula. It was as though the universe had been waiting for someone to discover its rhythm. At first, the scientific community regarded Planck's theory with polite skepticism. Few were ready to abandon the comfortable continuity of classical physics for something so strange. Even those who recognized the success of his formula hesitated to believe in the physical reality of quanta. The notion that energy itself was granular, that the smooth waves of light were built from individual bursts, seemed too radical, but the seeds had been planted, and in the years that followed, they began to grow. Planck continued to refine his ideas, delving deeper into the implications of quantization. He realized that the assumption of discrete energy exchange was not a simple mathematical convenience, but a reflection of the microscopic nature of matter itself. Every atom, he began to see, could vibrate only at specific frequencies, each corresponding to a distinct quantum of energy. When an atom absorbed heat, it stored energy in one of these discrete levels. When it cooled, it released that energy as radiation, one quantum at a time. In his lectures, Planck explained the concept with calm precision, but he rarely emphasized how revolutionary it truly was. To him, it was a necessary step toward reconciling theory with observation. To others, it was an opening into an entirely new dimension of thought. The world of physics had quietly changed, though few realized it yet. The beauty of Planck's quantum proposal lay in its universality. It was not limited to the behavior of heated bodies, it applied to all interactions between matter and energy. Every spark of light, every chemical reaction, every atomic transition followed the same rule: energy was quantized. This principle, though abstract, became the foundation of modern physics, the invisible framework that would later support Einstein's relativity, Bohr's atomic model, and the quantum mechanics of Schrödinger and Heisenberg. In the years immediately after Planck's discovery, the true power of the quantum idea began to unfold. Einstein seized upon it to explain the photoelectric effect, showing that light could eject electrons from metal surfaces only if its individual photons carried enough energy. That is, if their frequency, and therefore their quantum energy, was high enough. Suddenly, the quantum was no longer a mathematical curiosity, but a tangible force, measurable in the laboratory. What had begun as Planck's theoretical necessity had become an experimental reality. Planck himself remained modest in the face of this growing revolution. He often referred to his discovery as an act of desperation, claiming that he had not intended to overturn classical physics. Yet his act had opened the most profound chapter in the story of science. The concept of quanta changed not just physics, but the way humanity understood reality. No longer was the universe a continuous machine running on smooth gears of motion. It was a mosaic of discrete events, each governed by probabilities, each quantized in its existence. To appreciate the boldness of Planck's proposal, one must remember the intellectual climate of his time. Physics then was dominated by determinism, the belief that if one knew the position and velocity of every particle, one could predict the future of the entire universe. Energy, in that worldview, was a continuous ocean, flowing freely and infinitely divisible. Planck's quanta shattered that illusion. They introduced an atomic structure to energy itself. The old belief that nature could be understood purely through continuity collapsed under the weight of one small constant, h. Planck's constant may appear tiny, approximately 6.626 × 10 pi joule seconds, but its implications are cosmic. It defines the scale at which quantum effects dominate, where the strange rules of the microscopic world take over. To the naked eye, the world seems continuous because h is so small the gaps between quanta are imperceptible. But at the atomic level, those gaps become the rhythm of reality. Every electron, every photon, every atom dances to the beat of h. When Planck presented his paper on December 14, 1900, to the German Physical Society, he could not have imagined that this quiet meeting in Berlin would mark the birth of quantum theory. The audience listened respectfully as he explained his new formula, perhaps unaware that they were witnessing the beginning of a scientific revolution. To them, it was just another technical lecture. To history, it was the moment the universe revealed its hidden structure. After the talk, Planck returned home, exhausted but content. In his notes, he reflected on the strange beauty of the result. Though he could not yet explain why energy should be quantized, he felt certain that nature had spoken truth through mathematics. His constant h was not an invention, it was a discovery, the fingerprint of reality itself. Over time, the term quantum began to gain weight and meaning. It came to represent not just a packet of energy, but a new philosophy of nature. One where certainty dissolved into probability, where continuity gave way to discreteness. It invited scientists to see the world not as a single unbroken line, but as a pattern of dots, each distinct yet connected in harmony. The discrete nature of energy also explained phenomena far beyond blackbody radiation. It clarified the stability of atoms, the colors of light emitted by gases, and the spectral lines observed in laboratory experiments. Suddenly, the strange, isolated observations of 19th-century spectroscopy made perfect sense. Each color corresponded to a specific quantum jump within an atom. The mystery of why atoms emitted only certain wavelengths was no longer a puzzle. It was a natural consequence of Planck's principle. In retrospect, the idea of quantization appears almost inevitable. Yet, in its time, it required an extraordinary leap of imagination. Planck's willingness to accept discreteness, to think beyond the comfort of continuity, marked the dawn of modern physics. He had not merely solved an equation, he had opened a new dimension of thought. The world would never again be seen as smooth, predictable, or entirely knowable. Instead, it became a place of wonder, governed by rules that defied ordinary intuition but described reality with unmatched precision. And so, with his proposal that energy is emitted in discrete packets called quanta, Max Planck transformed the boundaries of science. His insight became the bridge between the known and the unknown, between the predictable world of the visible and the mysterious dance of the invisible. Through his discovery, he gave humanity a new way to look at light, matter, and existence itself, not as continuous streams, but as countless tiny steps in the eternal rhythm of the cosmos. As the 20th century dawned, the dust from Planck's daring proposal had yet to settle. His suggestion that energy was emitted and absorbed in discrete packets, quanta, was unlike anything science had ever encountered. Though Planck himself was cautious, the ripples of his idea began to spread quietly through the scientific world. At first, many dismissed it as a mathematical trick, a mere stopgap to patch the broken formulas of classical physics. Yet beneath this modest beginning, a revolution was brewing, one that would shatter the very framework of how humanity perceived light, matter, and the laws of nature. The essence of Planck's concept lay in a single, simple equation, eta, where represented the energy of radiation. H stood for a new constant, Planck's constant, and denoted the frequency of the radiation. What this meant, in essence, was that energy could not vary smoothly or continuously. It could only exist in multiples of this tiny, fundamental unit, energy quanta. This concept implied a discontinuity at the heart of nature itself, a sharp break in what had always been assumed to be continuous. The world Planck lived in did not easily accept such abrupt notions. For centuries, scientists had believed that energy, like time or space, flowed in an unbroken stream. Newton's mechanics, Maxwell's electromagnetic theory, and the smooth waves of light all confirmed this comforting view. The universe, it seemed, was a vast, predictable machine, where every event had a cause, and every cause led to an effect. But Planck's hypothesis introduced a strange irregularity, a place where nature acted in jumps rather than in flows. It was a bold intrusion into a realm that had been defined by certainty and order. Planck's own feelings toward his discovery were complex. In his notes and letters, he admitted that he considered the assumption of quantization to be a purely formal hypothesis. He did not initially believe that energy quanta existed physically. Rather, he saw them as a useful abstraction, an ingenious mathematical tool to fit the observed data. But science has a curious way of growing beyond the intentions of its creators. Once the idea of quantized energy entered the stage, it took on a life of its own, inviting new minds to explore its implications and question its limits. The first to take Planck's notion seriously was Albert Einstein. In 1905, Einstein extended Planck's hypothesis beyond thermal radiation to explain the photoelectric effect, the phenomenon where light striking a metal surface ejects electrons from it. Classical wave theory could not explain why light below a certain frequency, no matter how intense, failed to release any electrons. But Einstein proposed that light itself was made up of discrete packets of energy, later called photons, each carrying energy proportional to its frequency. This was Planck's idea, but bolder and more direct. For Einstein, quantization was not just a trick, it was reality. At first, Planck was uneasy with Einstein's interpretation. He had never meant to imply that light itself was quantized, only that the exchange of energy between matter and radiation occurred in discrete steps. Yet Einstein's paper marked the true birth of quantum theory, taking Planck's hesitant suggestion and turning it into a principle of nature. Over time, as more experimental evidence accumulated, Planck himself began to accept that his original hypothesis described something fundamentally real. The simplicity of Planck's law hid a depth that few could have imagined. In the classical view, a vibrating atom could emit or absorb any amount of energy. But under Planck's hypothesis, only specific frequencies were allowed, those corresponding to whole number multiples of the quantum of energy. This meant that the microscopic world was quantized at every level. The vibrations of atoms, the emission of light, the transitions of electrons, all occurred in fixed jumps. Imagine a pianist playing a melody. In the classical world, the piano would produce a continuous slide of sound from one note to another. But in the quantum world, each key produces only a discrete note, no in-between sounds exist. This is what Planck's idea did to physics. It replaced the smooth flow of energy with a staircase of distinct steps. The higher the frequency, the larger each step. It was a universe built not of continuity but of rhythm, structured, precise, and fundamentally granular. As the years passed, more evidence reinforced Planck's daring theory. The precise spectra of light emitted by heated gases matched perfectly with predictions made using quantization. Classical physics had failed utterly to reproduce these results. Moreover, the ultraviolet catastrophe that had haunted theoretical physics was now completely resolved by Planck's radiation law. His constant, h, became one of the most important quantities in all of science, a bridge between the macroscopic and the microscopic worlds. Yet Planck's discovery was not only a scientific triumph, it was a philosophical earthquake. The quantization of energy challenged the deep-seated belief that nature was entirely deterministic. The idea that energy could exist only in discrete packets suggested a kind of cosmic granularity, a hidden randomness at the foundation of reality. It hinted that the laws of nature might not be as smooth or predictable as once thought. Later, when quantum mechanics fully developed, this sense of uncertainty would explode into a complete reimagining of causality itself. For Planck, who valued order, logic, and continuity, this was unsettling. He was a man of discipline and precision, devoted to uncovering the harmony of the cosmos. The idea that the universe contained an element of randomness was, to him, deeply uncomfortable. Yet he accepted it because the evidence demanded it. His loyalty to truth outweighed his attachment to tradition. In this way, Planck exemplified the very spirit of science, following the data, even when it leads into uncharted territory. In the laboratories of Europe, young physicists were beginning to take notice. They recognized that Planck's formula was not a mere curiosity, but the seed of a new paradigm. Niels Bohr, for instance, applied the concept of quantized energy to the atom, proposing that electrons could orbit the nucleus only in fixed energy levels. When they jumped from one level to another, they emitted or absorbed a quantum of light, a photon, whose energy matched the difference between the levels. Once again, Planck's constant was at the heart of the calculation. The atomic world, which had once seemed chaotic and invisible, now revealed an astonishing order built upon quantized laws. The colors of stars, the glow of heated metals, the functioning of semiconductors, all could be traced back to Planck's tiny constant. The idea that energy existed in indivisible packets connected the behavior of the smallest particles with the most distant galaxies. From the heat of the sun to the light of a candle, the same law governed the flow of energy through the universe. What made Planck's insight so extraordinary was that it came not from intuition or imagination alone, but from a desperate attempt to solve a stubborn problem. He did not set out to invent quantum theory, he stumbled upon it in his effort to save classical physics. This irony is one of the great paradoxes of scientific progress, that revolutionary ideas often emerge from attempts to preserve the old order. Planck's quantization of energy was both a rescue and a rebellion, a bridge between two worlds. Over time, the concept of the quantum evolved from a mathematical device into the foundation of an entirely new branch of physics. Experiments confirmed again and again that nature did not behave continuously. Whether in the emission of light, the conduction of electricity, or the motion of electrons, the universe revealed itself as fundamentally quantized. The implications were immense. Technology itself began to transform under the power of quantum principles. But perhaps the most profound aspect of Planck's idea was its philosophical depth. It forced scientists to confront the limits of human perception and reasoning. The classical world of smooth transitions and predictable laws was an illusion, a simplification of a deeper, more fragmented truth. Beneath the surface, reality pulsed in discrete rhythms, each quantum a heartbeat of the cosmos. By the time Planck received the Nobel Prize in 1918, his theory had already become the cornerstone of a growing quantum revolution. Yet he remained modest about his contribution, often downplaying its significance. He once remarked, "I did not seek the quantum. It forced itself upon me." It was as if he had merely opened a door and glimpsed a landscape far larger than he could ever have imagined. In the decades that followed, Planck's quanta became the building blocks of modern physics. Quantum theory expanded into quantum mechanics, quantum electrodynamics, and eventually quantum field theory, each extension unveiling new mysteries of the subatomic world. Every advancement in this vast field owed its existence to that single, radical idea that energy comes in discrete packets. From lasers to transistors, from solar cells to quantum computers, the fingerprints of Planck's discovery are everywhere. Each photon that illuminates a room, each electron that powers a circuit, each atom that emits light, all follow the rhythm of Planck's constant. The entire modern world, in some sense, is built upon the quanta he first conceived in 1900. And yet, beyond the science, there lies a poetic truth. Planck's discovery reminds us that even the smallest, most invisible elements of the universe operate according to profound and elegant principles. It tells us that simplicity and beauty often hide within complexity. The quantum is not just a unit of energy. It is a symbol of how human understanding can leap beyond the visible into realms once thought unreachable. Max Planck's proposal that energy is emitted in discrete quanta was more than a theory. It was a doorway into a new reality. Through it, humanity learned that the universe is not a continuous ocean, but a symphony of tiny notes, each one distinct yet harmoniously intertwined. From that moment onward, physics was never the same. The classical world gave way to the quantum, and with it came an era of wonder, discovery, and transformation, a revolution born from a single spark of insight. In the quiet corridors of theoretical physics at the dawn of the 20th century, a single number began to whisper through the scientific world, a number so small, so abstract, that few could grasp its meaning. It was called Planck's constant, a symbol of something new and profound, something that would alter the course of science forever. What had begun as Max Planck's attempt to fix a flaw in classical theory had now given birth to a constant that defined the smallest indivisible unit of energy. Like a hidden rhythm in the universe, it dictated how light, matter, and energy interacted at their most fundamental levels. When Planck first introduced his constant, h, he did not fully realize what he had uncovered. He was simply searching for a mathematical solution to explain how energy radiated from hot objects, the Blackbody problem. To fit the data, he needed to assume that energy was not continuous but came in discrete packets, proportional to the frequency of the radiation. That proportionality factor, which made his formula work, was Planck's constant. In essence, eta became the doorway to quantum theory. This constant was extraordinarily small, approximately 6.66 × 10 joule-seconds. To the macroscopic world of human experience, that seemed insignificant, even meaningless. But within the atomic realm, it carried infinite weight. It represented the graininess of the universe, the smallest possible increment by which energy could change. It was as if nature herself operated on a delicate grid, with Planck's constant defining the spacing between its lines. At first, few could comprehend the enormity of this concept. Planck himself viewed h as a mathematical necessity, not a physical revelation. Yet the constant possessed a quiet authority. It began to appear everywhere, in equations that described not just light, but the behavior of atoms, electrons, and the very structure of matter. What had seemed a patchwork solution soon revealed itself as the foundational pillar of a new physics. To appreciate the magnitude of Planck's constant, one must imagine the universe as a vast ocean of energy. Classical physics assumed this ocean flowed smoothly, with waves of every possible height. But Planck discovered that the waves could not take any arbitrary size. They were built of quanta, tiny packets of energy, and the size of each packet was determined by his constant. In this view, the universe was not continuous but pixelated at the most fundamental level, each pixel a quantum defined by h. The constant soon became the cornerstone of a profound new reality. Every particle, every wave, every interaction between light and matter adhered to its rule. It told scientists how much energy a photon of light carried, how electrons moved within atoms, and how the smallest vibrations of molecules occurred. It connected the microscopic with the macroscopic, bridging the invisible dance of particles with the world we perceive. Planck's constant also carried philosophical implications that shook the scientific establishment. If energy came only in discrete units, then nature's behavior was not infinitely divisible. This challenged centuries of belief that the universe operated like a perfectly smooth machine. The realization that there was a smallest step, a minimal energy change, implied that reality itself had a built-in limit to precision. Nature was no longer continuous, it was quantized. For the first time, physicists began to recognize that Planck's constant represented more than a number. It was a cosmic scale factor. It determined where classical physics ended and quantum behavior began. When the quantities involved were large compared to h, the old laws of Newton and Maxwell worked perfectly. But when the energies were small, on the order of h, the classical laws broke down, and the strange, probabilistic world of quantum mechanics took over. Planck's constant was the boundary stone marking the frontier between the familiar and the mysterious. In 1905, Einstein deepened the meaning of H when he applied it to his explanation of the photoelectric effect. He proposed that light was composed of quanta, later called photons, each carrying energy equal to h. This bold leap gave Planck's constant a physical reality. It was no longer just a mathematical fudge factor, but a measurable quantity that determined how light interacted with matter. Experiments confirmed Einstein's predictions with striking accuracy, and suddenly h became one of the most important constants in all of physics. Over the following decades, scientists found that Planck's constant was woven into every aspect of quantum theory. In the Bohr model of the atom, for instance, electrons could occupy only certain orbits, each corresponding to a specific multiple of h. The difference between these orbits determined the frequency of light emitted or absorbed when an electron jumped from one level to another. This explained the discrete lines seen in atomic spectra. Each color of light corresponded to a quantum transition governed by Planck's constant. In this way, h became the heartbeat of the atomic world. It defined how atoms absorbed and emitted light, how chemical reactions released energy, and how matter behaved at its most fundamental level. It was the thread connecting all of nature's patterns, from the glow of stars to the hum of electrons in a metal wire. But beyond its practical utility, Planck's constant carried an almost mystical significance. It represented a kind of cosmic fingerprint, a universal signature embedded in the fabric of existence. Wherever scientists looked, whether in the vast emptiness of space or in the smallest subatomic particles, h appeared as the measure of quantization. It told us that nature was not arbitrary, but structured, not infinitely divisible, but discrete. It was as though the universe spoke in the language of quanta, and h was the letter by which it spelled reality. Planck himself often reflected on the strange duality of his discovery. He had started from the deterministic world of classical physics, believing that nature followed continuous, predictable laws. Yet his constant introduced an element of discontinuity, even unpredictability. He called it a desperate act, but history would later see it as a stroke of genius. Through h he had revealed that certainty had limits, and that at the smallest scales, reality was governed by probabilities and jumps rather than smooth transitions. The constant soon became the cornerstone for Werner Heisenberg's uncertainty principle, which states that one cannot know both the position and momentum of a particle with absolute precision. The limit of this precision is determined by, once again, Planck's constant. It was h that dictated how uncertain nature could be, how much knowledge was fundamentally inaccessible. The constant, so small in numerical value, represented a vast boundary between what can and cannot be known. To visualize its importance, imagine standing at the threshold between two worlds. On one side lies the world of everyday experience, continuous, predictable, governed by classical laws. On the other lies the quantum realm, where particles flicker in and out of certainty, and probabilities replace certainties. Planck's constant is the doorway between them, the silent guardian of both domains. When measured experimentally, h demonstrated remarkable consistency. It became one of the defining constants of physics, alongside the speed of light and the gravitational constant. Together, these numbers formed the backbone of modern scientific understanding. In 2019, over a century after Planck's discovery, the kilogram itself was redefined in terms of Planck's constant, anchoring our system of measurement to this quantum foundation. What began as an obscure constant in thermal radiation theory had now become a fundamental measure of reality itself. This transition from curiosity to cornerstone illustrates the transformative power of Planck's idea. Through h, scientists learned that the universe operates according to hidden rules of scale and proportion. It showed that energy, time, and motion were linked in ways far beyond the grasp of classical thought. Every equation in quantum mechanics, from Schrödinger's wave function to Dirac's equations of matter, carries h at its core. Without it, the quantum world collapses into incomprehensibility. As the new physics evolved, h became not only a tool of measurement, but a symbol of the limits of human knowledge. It told us that there is a smallest possible action in the universe, a fundamental granularity that defines the rhythm of existence. No matter how fine our instruments or how deep our theories, we cannot escape the quantum of action that Planck revealed. It is the minimal flicker of causality, the smallest breath of the cosmos. Even in fields far from atomic physics, the influence of Planck's constant can be felt. In cosmology, it defines the Planck scale, a realm of unimaginably small distances and energies where gravity and quantum mechanics merge. At this scale, 10 meters, the universe behaves in ways we cannot yet describe, a region where spacetime itself may become quantized, the constants that define our reality. Planck's constant, the speed of light, and Newton's gravitational constant combine to set the limits of the possible. It is humbling to think that a constant so small governs everything so large. The burning of stars, the emission of light, the behavior of molecules, all dance to the same quantum rhythm. Planck's constant, invisible yet omnipresent, orchestrates the energy exchange across the universe. By the early 20th century, physicists began to realize that this constant was not merely a numerical value, it was a window into the architecture of nature. The quantum of action symbolized the smallest building block of change. Every interaction, every vibration, every photon, every electron transition carried the mark of h. It was as if the entire universe pulsed in harmony with a single, universal beat, steady and eternal. The legacy of Planck's constant goes beyond equations and laboratories. It represents a shift in human perception, a recognition that beneath the surface of continuity lies a discrete pulse of reality. In this revelation, Planck bridged two worlds, the deterministic order of classical physics and the probabilistic uncertainty of the quantum domain. Through his constant, he gave humanity not only a new science, but a new philosophy of existence. And though Max Planck himself could never have foreseen the vast scope of what he had uncovered, his constant stands today as one of the greatest intellectual achievements in human history. It is the key that unlocked the atom, the foundation of quantum mechanics, and the measure of the universe's smallest whisper of energy. As the echo of Planck's discovery spread through the scientific world, his constant began to reveal secrets far beyond what even he could have imagined. It was not merely a number confined to Blackbody radiation. It became a universal signature of nature's smallest actions. Every phenomenon in the quantum realm seemed to whisper its name. Planck's constant was not just a measure. It was the very heartbeat of the universe at its most fundamental level. The brilliance of h lies in its universality. It doesn't belong to any single branch of science, it transcends them all. Whether one studies the emission of light, the vibration of atoms, or the strange behavior of electrons in metals, h appears as the silent law that governs them. It tells us that every exchange of energy, every transition, every flicker of motion in the quantum world occurs in multiples of this constant. It defines the scale at which nature begins to show her granular structure, where the smooth flow of energy breaks into discrete quanta. In the early years of the 20th century, this realization began to reshape every corner of physics. The old certainties were crumbling. Newton's clockwork universe, built upon continuity and determinism, was being replaced by a probabilistic and quantized cosmos. Scientists had to unlearn the habits of centuries, to think not in terms of infinite divisibility, but in jumps and steps, quantum leaps defined by h. It was as if the universe itself spoke in rhythm, each beat marked by Planck's constant. One of the most striking examples of this new rhythm came from the atomic world. When Niels Bohr applied Planck's constant to his model of the hydrogen atom, a miraculous order emerged. Bohr proposed that electrons orbit the nucleus only in certain allowed paths, and that the angular momentum of these electrons must be an exact multiple of h. Suddenly, the mysterious patterns of light emitted by hydrogen, the spectral lines, made perfect sense. Each color corresponded to a transition between orbits, each transition releasing a quantum of energy equal to h. Here, Planck's constant did something extraordinary. It connected the abstract with the visible. It linked the invisible dance of electrons with the brilliant colors of light that reach our eyes. The constant became a bridge between the unseen and the seen, the microscopic and the cosmic. Through H, scientists could now describe why stars shine, why metals glow when heated, and why each element emits its own unique spectrum. But Planck's constant went even deeper. It wasn't just about light or atoms. It became the foundation of all quantum behavior. In Louis de Broglie's daring theory of wave-particle duality, H connected the momentum of a particle with its wavelength. This meant that even solid matter, electrons, protons, entire atoms, had a wave like nature. The classical boundary between particle and wave dissolved, replaced by a shimmering duality. The wavelength of these matter waves was inversely proportional to momentum, with h as the proportionality constant. Once again, Planck's constant stood at the center, tying together two seemingly opposite ideas into a single truth. As the quantum revolution deepened, h appeared everywhere, like a hidden signature of reality. In Werner Heisenberg's uncertainty principle, it marked the limit of what could be known. One could not measure both the position and momentum of a particle with infinite precision, because the product of these uncertainties could never be smaller than he4y. It was as if nature herself had drawn a curtain, a boundary beyond which no knowledge could pass. Planck's constant set that boundary. It defined the horizon of human comprehension, the line between the measurable and the unknowable. For Erwin Schrödinger, too, h was indispensable. In his wave equation, the very foundation of quantum mechanics, Planck's constant defined how the wave function of a particle evolved through time and space. Without it, the equation collapses and the quantum world becomes mute. Every probability, every quantum state, every interaction between particles depends on the presence of h. It is the pulse that gives life to the mathematics of the microscopic universe. In time, Planck's constant began to shape not only theory but technology. Its implications rippled outward into inventions that transformed civilization. The understanding of photons led to the creation of lasers, beams of coherent light whose precision and intensity come directly from quantum mechanics. Transistors, the tiny switches that form the foundation of all modern electronics, operate based on quantum tunneling, another phenomenon governed by h. Even the silicon chips that power computers rely on principles that trace their lineage back to Planck's tiny constant. The story does not end there. In the realm of chemistry, h determines how atoms bond and how molecules vibrate. The colors of the world, the functioning of photosynthesis, the very processes of life, all depend on energy exchanges measured in quanta of lum. In medicine, magnetic resonance imaging (MRI) relies on quantum transitions defined by Planck's constant. In communication, fiber optics transmit information through photons that obey Planck's laws. The digital age itself is, in essence, the age of the quantum. And yet, beyond all these applications, Planck's constant remains a symbol of humility, a reminder of how small we are in the face of the cosmos. Its magnitude, 6.626 altendan, is a whisper of energy, a fraction of a joule. But within that whisper lies the structure of the universe. It is as though creation itself is composed of tiny syllables of energy, each one measured by h. For Planck, this discovery was not a triumph of ego, but an act of faith in nature's order. He once said, "A new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die, and a new generation grows up that is familiar with it." He knew that his constant would outlive him, and indeed, it did. It grew from a controversial hypothesis into the cornerstone of all modern physics. By the mid-20th century, Planck's constant had become one of the fundamental constants of nature, alongside the speed of light as c, and the gravitational constant as g. Together, these constants form the bedrock of our understanding of reality. In fact, physicists discovered that one could construct an entire system of natural units, called the Planck units, based solely on h, c, and g. These units define the scales of the universe itself: the Planck length, the Planck time, the Planck temperature, and the Planck energy. The Planck length, for instance, is unimaginably small, about 1.665 meters, the distance below which our understanding of space and time breaks down. The Planck time, 539 seconds, is the shortest possible interval of time that can exist. Beyond these limits, the fabric of spacetime itself becomes uncertain. Thus, Planck's constant defines not just energy, but the ultimate boundaries of the universe. It tells us that there is a smallest measurable length, a shortest duration, and a highest possible energy, all set by the quantum of action that bears Planck's name. The philosophical implications are staggering. The constant suggests that even space and time may not be continuous but composed of tiny, indivisible units. It points toward a universe built not from smooth curves but from discrete quanta, each moment a flicker, each location a pixel in the grand design of reality. This view blurs the line between physics and metaphysics. It suggests that the cosmos, at its core, may be both digital and analog, continuous in perception, yet quantized in essence. When Planck first derived his constant, he was unaware that he had uncovered this cosmic code. He sought only to describe how objects radiate energy. But in that pursuit, he stumbled upon the foundation of everything. His H would one day explain the structure of atoms, the birth of stars, the collapse of black holes, and perhaps even the origin of the universe itself. Today, Planck's constant is woven into the very fabric of our measurement systems. In 2019, it was used to redefine the kilogram, the fundamental unit of mass. Instead of relying on a physical object stored in a vault in France, the kilogram is now defined in terms of Planck's constant, the speed of light, and the cesium frequency. The act of redefining the kilogram based on h was more than a technical update. It was a philosophical statement. Humanity had anchored its measure of matter to the quantum heartbeat of the universe. The constant also continues to inspire theoretical exploration. In modern physics, researchers search for ways to unify quantum mechanics with general relativity, the theory of gravity. They believe that at the Planck scale, where energies and distances are defined by h, these two great frameworks will merge into a single, coherent description of reality. Whether through string theory, loop quantum gravity, or other models, Planck's constant remains the central clue. It is the thread that scientists follow into the deepest mysteries of existence. In the poetic sense, h represents balance, the harmony between the infinite and the finite. It tells us that while energy can be vast, it still comes in tiny, indivisible notes. Like a symphony built from discrete tones, the universe performs its grand composition in quanta. Each photon, each electron, each atom contributes a single note to this cosmic song, and h is the measure of the rhythm that binds them. When we gaze at the stars, the light that reaches our eyes has traveled across billions of years, each photon carrying an energy defined by Planck's constant. Every glimmer in the night sky, every pulse of radiation, every spark of creation is a reminder of the same principle. The universe speaks through quanta, and h is its alphabet. In the end, Max Planck's constant did more than solve a problem in thermal radiation. It opened humanity's eyes to the quantized nature of existence itself. It showed that the world is not infinitely divisible, that there are natural limits to what can be known, measured, and changed. It revealed that beneath the apparent continuity of experience lies a pulse, a flickering rhythm that defines reality's structure. Planck once remarked that science advances, one funeral at a time, but his constant outlived not only its skeptics, but the entire framework of classical thought. It became the cornerstone of modern physics, guiding generations of scientists toward deeper truths. And as long as humanity continues to explore the mysteries of the cosmos, h will remain its silent companion, the constant that binds light, matter, and energy into the grand dance of existence. From the faintest photon to the mightiest black hole, from the hum of atoms to the vast cosmic background radiation, everything obeys the same immutable law. Energy comes in quanta, and those quanta are measured by Planck's constant. It is the scale of creation itself, the smallest step by which the universe moves forward. Through this single, elegant number, Max Planck not only changed physics, he changed our perception of reality. In his constant, the universe found its voice, and in that voice humanity discovered the rhythm of existence, quantized and eternal. When Planck introduced his revolutionary idea of energy quanta, he did not just propose a mathematical trick. He solved one of the greatest scientific crises of his time, the ultraviolet catastrophe. This catastrophe was not a physical explosion, but a theoretical one, a breakdown of classical physics that left scientists puzzled and frustrated. According to classical theory, when an object was heated, it should emit radiation in a continuous range of wavelengths. The equations derived from 19th century physics predicted that as the wavelength became shorter, toward the ultraviolet region, the emitted energy should increase without limit. In other words, a hot object would release infinite energy at high frequencies, something that clearly contradicted both reason and experiment. No furnace, no star, no atom could behave this way, yet the mathematics of classical physics insisted it must. Physicists at the turn of the 20th century were haunted by this paradox. Experiments showed that radiation from a blackbody, an idealized perfect emitter, actually peaked at a certain frequency and then diminished at shorter wavelengths. Classical physics, elegant and precise as it had been for centuries, was failing to describe something as basic as heat and light. The failure wasn't minor, it was catastrophic. The ultraviolet catastrophe was a warning sign that the old worldview of continuous energy and absolute determinism was incomplete. It was here, in this chaos of conflicting equations and failed predictions, that Max Planck stepped forward. Planck was a man of precision and logic, someone who believed deeply in the order of nature. For years, he tried to fit the experimental data using the trusted laws of thermodynamics and electromagnetism, but nothing worked. In 1900, he decided to take a radical step. He introduced a new mathematical assumption, not because he believed it reflected reality, but because it fit the data. He proposed that energy could only be emitted or absorbed in discrete packets, or quanta, proportional to the frequency of the radiation. This meant that instead of a continuous stream, energy came in tiny steps. The higher the frequency, the larger the step, given by the relation E to him, where h was a new constant of nature, the Planck constant. When Planck applied this idea to the blackbody radiation problem, the results were astonishing. His equation perfectly matched the experimental data across all frequencies. The predicted curve now rose, reached a peak, and fell off smoothly in the ultraviolet region, exactly as observed. The dreaded infinity vanished. The catastrophe was averted. For the first time, the behavior of radiation could be described consistently across all wavelengths. Planck's formula united theory and experiment in a way no one had thought possible. Yet, Planck himself was cautious. He saw his constant h as a mere mathematical device, not a reflection of reality. But as years passed, others began to see that his quanta were not just convenient symbols, they were real. Einstein in 1905 took Planck's idea further, suggesting that light itself was made up of particles, photons, each carrying a quantum of energy, F-ular. What had begun as an act of mathematical desperation had opened the door to quantum physics. The resolution of the ultraviolet catastrophe marked the dawn of a new era. It showed that at very small scales, nature did not follow the smooth curves of classical laws but the sharp, stepped behavior of quanta. The continuous world of Newton was replaced by a discrete universe, governed by probabilities and packets of energy. This insight revolutionized not only theoretical physics, but also the way scientists viewed reality itself. Planck's success was not just in solving a technical problem, it was in revealing a deeper truth about nature. He had shown that the energy of the universe was not an unbroken flow, but a collection of pulses, each defined by his constant h. This discovery explained why objects glow red, then yellow, then white as they heat up, why the stars radiate in specific patterns, and why matter behaves differently at microscopic scales. The ultraviolet catastrophe became a turning point in human understanding. It was the moment when physics moved from the realm of certainty to the realm of mystery and discovery. Planck's formula bridged the gap between observation and theory, between the known and the unknown. It was not just a rescue mission for classical physics, it was the birth of modern physics itself. From that point onward, every step in the quantum journey, from Einstein's photoelectric effect to Bohr's atomic model and beyond, traced its roots back to Planck's resolution of the ultraviolet catastrophe. His bold leap had tamed infinity and given scientists the first glimpse of a quantized universe. What had once been a scientific crisis became the foundation for the technologies and theories that define our modern world. In the soft glow of that breakthrough, one can almost imagine Planck at his desk in Berlin, staring at the strange new formula that fit the world so perfectly, not yet realizing that he had uncovered the key to the quantum realm. The catastrophe had not destroyed physics, it had transformed it. Through the quiet precision of Planck's constant, the chaos of the ultraviolet catastrophe gave way to the harmony of quantum order, forever changing our understanding of light, energy, and the very structure of the universe. The discovery of Planck's quantum theory did not just solve a scientific mystery, it transformed the entire understanding of light and energy, opening a doorway to a new universe of thought. Before Planck, light was seen only as a wave, a continuous ripple moving through space. But with the concept of quanta, light gained a dual identity. It could behave both as a wave and as a particle, depending on how it was observed. This dual nature became one of the most extraordinary revelations in science, something that defied intuition yet perfectly described nature's behavior. The energy of radiation was no longer a smooth, flowing stream but a collection of distinct packets, each carrying a specific amount of energy determined by Planck's constant. In 1905, Albert Einstein took Planck's hypothesis further, suggesting that light itself was composed of individual quanta, later called photons. He used this idea to explain the photoelectric effect, a phenomenon that had puzzled scientists for years. When light of a certain frequency struck a metal surface, it ejected electrons, but if the light's frequency was below a threshold, no electrons were emitted no matter how intense the light was. Classical physics could not explain this. It predicted that the energy of emitted electrons should depend only on the brightness of the light, not its color. But experiments showed otherwise. The mystery deepened until Einstein proposed that each photon carried energy proportional to its frequency, eta lun. Only photons with enough energy, those of higher frequency, could knock electrons free. This simple yet profound insight confirmed Planck's theory and revolutionized physics once again. It showed that light had a particle, like nature, carrying discrete quanta of energy. Suddenly, Planck's constant appeared not just in theoretical equations, but in real, measurable phenomena. The photoelectric effect proved that energy quanta were not a mathematical abstraction. They were a physical reality. The experiment became a cornerstone of modern physics, and Einstein's work on it would eventually earn him the Nobel Prize. The implications of this were staggering. Light, which had for centuries been understood as a wave, now revealed its particle side. It could behave like a continuous wave when spreading through space, but act like a particle when interacting with matter. This duality became one of the most profound and mysterious features of the universe, challenging all notions of determinism and classical predictability. Physicists were forced to accept that light and matter existed in a state that was neither purely wave nor purely particle, but both, a strange, hybrid reality defined by probability and interaction. As this new understanding spread, scientists began to see that the quantum concept applied not only to light, but also to matter itself. The energy of electrons orbiting an atom could only exist in quantized levels, just as Planck's theory described for radiation. This realization became the foundation for Niels Bohr's model of the atom, where electrons moved in fixed orbits, emitting or absorbing photons as they jumped from one level to another. Each transition released or absorbed a quantum of energy equal to a joule. Thus, Planck's constant became the link between the motion of particles and the energy of light, the universal bridge connecting the two worlds. This dual nature of light changed how scientists perceived the universe. It was no longer a place governed by rigid, continuous laws but a dynamic interplay of possibilities. The wave-particle duality showed that the universe operated with a subtle balance between certainty and uncertainty. Light could interfere with itself like a wave, creating patterns of brightness and darkness, yet it could also arrive at a detector as a single photon. Nature, it seemed, did not choose one identity over the other but embraced both simultaneously. In laboratories across the world, this concept gave birth to new experiments that pushed the boundaries of human understanding. The famous double-slit experiment revealed the full mystery of quantum behavior. When light passed through two narrow slits, it created an interference pattern on the screen beyond, proof of its wave-like nature. But when detectors were used to observe which slit each photon passed through, the pattern vanished, and light behaved like particles. The act of observation itself seemed to influence reality, a notion that challenged the very foundations of science and philosophy alike. This was the dawn of quantum mechanics, a world where probabilities replaced certainties and where observation and reality were intertwined in ways no one had expected. Planck's idea, born from the need to explain the radiation of heated bodies, had grown into a universal principle shaping everything from atomic energy levels to the structure of stars. The concept of light quanta became the key to understanding not only the microscopic realm, but also the vastness of the cosmos. From lasers to solar cells, from quantum computers to the technologies that power communication satellites, the legacy of Planck's quantum theory is everywhere. The understanding that energy comes in discrete packets made possible the manipulation of light and matter at their most fundamental levels. Each photon, governed by Planck's constant, carries the potential to transform energy into information, fueling the technological and scientific revolutions of the modern age. And yet, beneath all the complexity and the mathematics, the beauty of the discovery lies in its simplicity, that nature operates not in an unbroken flow, but in rhythmic steps, each one defined by the quantum of action. Planck's theory of elementary quanta revealed that the smallest scales of the universe were alive with structure, with rules so delicate and precise that they underpin everything from the colors we see to the life we live. It is a reminder that even the smallest constant can hold the power to reshape the universe, that in the quiet pulse of Planck's H, the light of understanding forever changed how humanity sees the world. The acceptance of Planck's theory marked not the end of a discovery, but the beginning of a revolution that would redefine physics, philosophy, and human understanding itself. When scientists began to realize the full implications of quantized energy, they saw that Planck's idea was not an isolated phenomenon, it was the foundation of an entirely new framework. Classical physics, which had ruled for centuries under the laws of Newton and Maxwell, was built on the belief that nature operated in continuous, predictable patterns. But Planck's constant introduced a fundamental limit, a smallest possible unit of energy, suggesting that the universe was granular at its core. This shattered the illusion of smooth continuity and replaced it with a new vision of reality, one governed by discrete jumps, probabilities, and uncertainty. In the years that followed, this vision evolved into quantum mechanics, a field that would transform every aspect of science. The pioneers of this new physics, Einstein, Bohr, Schrödinger, Heisenberg, and Dirac, each built upon the foundation Planck had laid. They explored what it meant for energy, light, and matter to behave in quanta, and their discoveries revealed a universe far stranger than anyone had imagined. Matter itself was found to exhibit dual characteristics, behaving both like particles and waves, bound by probabilities rather than fixed certainties. The deterministic laws of the past gave way to statistical ones, where outcomes could only be described by likelihood, not absolute prediction. The concept of energy quantization led to Bohr's atomic model, which explained why atoms emit light at specific frequencies rather than a continuous spectrum. This model showed that electrons could only occupy certain orbits, and when they jumped between these orbits, they emitted or absorbed energy in discrete quanta determined by Planck's constant. What had once been an abstract idea became a physical reality at the heart of atomic structure. This understanding gave rise to spectroscopy, allowing scientists to read the fingerprints of elements in stars and distant galaxies. Every color of light in the night sky was now a message from atoms, each photon a quantum of energy born in accordance with Planck's law. Heisenberg's uncertainty principle, another direct outcome of the quantum revolution, further deepened the mystery. It stated that one could never know both the position and momentum of a particle with perfect precision. The more accurately one was known, the less certain the other became. This was not a limitation of measurement, but a fundamental property of nature itself. Planck's constant defined the boundary of this uncertainty. It was a reminder that reality was not as solid or absolute as it appeared. It pulsed with a hidden rhythm of probabilities and fluctuations. Schrödinger, meanwhile, introduced his famous wave equation, describing how the quantum state of a system evolves over time. In this equation, Planck's constant again appeared as the bridge between the measurable world of energy and the abstract world of probability. The universe, once seen as a precise machine, now looked more like a grand symphony of waves, each governed by the rules of quantization. These waves did not describe particles moving along fixed paths, but probabilities of where they might be found, a concept that forever changed how scientists viewed matter and motion. Dirac extended these ideas to the realm of relativity, uniting Einstein's theory with quantum principles. His equations predicted the existence of antimatter, showing that every particle had a mirror image with opposite charge. Once again, Planck's constant stood at the heart of the relationship, linking energy, momentum, and frequency in the same elegant form. The quantum theory was no longer a patch for old physics. It had become a universal language, one that described everything from the smallest subatomic particles to the behavior of radiation and energy in the cosmos. As the 20th century progressed, the practical applications of Planck's discovery became visible everywhere. The understanding of quantum mechanics gave birth to transistors, semiconductors, lasers, and nuclear energy. The digital world, communication networks, and medical technologies all trace their origins back to the quantization of energy. The same constant that once appeared as a mathematical curiosity became the cornerstone of modern civilization. Each photon that powers a laser, each bit of data transmitted across the globe, is a living echo of Planck's insight. Yet beyond technology, the philosophical impact of this revolution was equally profound. The quantum world defied classical logic. It suggested that reality was not fixed until observed, that the act of measurement itself influenced the outcome. Bohr's principle of complementarity captured this paradox beautifully. Light and matter could be described as waves or particles, but never both simultaneously. What we observe depends on how we choose to observe it. This idea blurred the boundary between the observer and the observed, between human consciousness and physical reality. The universe, it seemed, was not a passive stage but a dynamic interaction between knowledge and existence. In the grand cosmic picture, Planck's theory revealed that everything, matter, energy, space, and time, is quantized at the deepest level. Even the vacuum, once thought to be empty, teems with fluctuations of energy, virtual particles appearing and disappearing in accordance with quantum laws. The same constants that govern the behavior of photons in a laboratory also dictate the birth of stars and the radiation of black holes. Stephen Hawking's discovery that black holes emit radiation, a phenomenon now called Hawking radiation, is directly linked to Planck's quantization principle. Thus, from the smallest particles to the largest cosmic structures, the signature of H is everywhere. The quantum revolution born from Planck's constant reshaped not only science but the very way humanity perceives the universe. It taught us that certainty is an illusion, that at the deepest level, existence is defined by possibility. It showed that even chaos follows laws, subtle and precise, written in the language of quanta. In Planck's theory, nature revealed her most intimate secret, that creation unfolds not in continuous streams, but in pulses of energy, each a tiny heartbeat of the cosmos. Max Planck once said he did not set out to destroy classical physics but to save it. Yet his discovery built an entirely new foundation instead. From that moment, physics was never the same. The constant H became the emblem of a new era, the quantum age, where the boundaries of the possible expanded beyond imagination. The world of quanta is invisible to the naked eye, yet it governs every breath of existence, from the flicker of a flame to the rhythm of the stars. Through it, humanity learned that even the smallest constant can contain the infinite, and that the universe itself, in all its vastness, is composed of countless tiny steps, each one a whisper of Planck's discovery, echoing through time. As the quantum revolution matured, Max Planck's theory of elementary quanta grew far beyond its original purpose. What began as an attempt to explain how hot objects emit light evolved into a universal principle that reshaped every branch of science. The seventh keynote, highlighting how Planck's ideas became the foundation for modern physics and technology, captures the true magnitude of his discovery. The quantum theory did not remain confined to laboratories or equations. It became the invisible framework upon which the modern world was built. Every beam of light, every electronic device, every scientific law at the smallest scales bears the imprint of Planck's constant. After Planck's discovery, a generation of physicists carried his ideas forward, transforming them into the pillars of a new scientific era. Quantum mechanics was no longer a theory. It was the language of the universe. It revealed that everything, from the tiniest subatomic particle to the largest star, operates through quantized interactions. The smooth, continuous universe of classical physics had given way to a world of discrete packets, energy levels, and probabilities. This change in perspective not only solved old mysteries, but opened doors to new realities that would forever alter human life. One of the most remarkable transformations came through technology. The quantum understanding of electrons led directly to the development of semiconductors, the foundation of modern electronics. Transistors, the tiny switches that process information in computers, smartphones, and satellites, rely on the controlled flow of electrons through materials governed by quantum laws. Without Planck's constant defining how energy levels behave, this control would be impossible. The entire digital world, every byte of data, every signal transmitted, exists because of the quantization of energy that Planck first proposed in 1900. The impact of quantum theory extended into the realm of light and communication as well. The invention of the laser, a device that emits light through the stimulated emission of photons, was a direct consequence of Planck's idea. Each photon in a laser beam is identical in energy and phase, moving in perfect harmony. Lasers became essential tools in medicine, manufacturing, telecommunications, and research. They perform delicate eye surgeries, scan barcodes in stores, and transmit data through optical fibers that circle the globe. The coherence of the laser is nothing less than a symphony of photons, dancing to the rhythm of Planck's constant. Quantum mechanics also revolutionized the understanding of matter and energy at the nuclear level. It explained how atoms hold together, why certain elements are stable, and how others release enormous energy when their nuclei are split or fused. The development of nuclear power and the exploration of atomic energy, though fraught with both hope and danger, stemmed from this same quantum understanding. Planck's discovery of energy quanta laid the mathematical foundation for understanding how energy is stored and released within the heart of matter itself. In the field of chemistry, quantum theory revealed the hidden patterns that govern molecular bonds. It explained why water has its unique properties, why metals conduct electricity, and how light interacts with matter to create color and heat. Quantum chemistry became the key to developing new materials, medicines, and technologies. From superconductors to nanotechnology, the ability to manipulate the quantum properties of matter has allowed humanity to engineer materials once thought impossible, metals that conduct electricity with zero resistance, and structures so small they operate at the scale of individual atoms. In astronomy and cosmology, Planck's legacy shines just as brightly. Quantum mechanics helps explain the birth and death of stars, the radiation left over from the Big Bang, and the mysterious behavior of black holes. The early universe itself is believed to have been governed by quantum fluctuations, tiny irregularities that later grew into galaxies and clusters of stars. Even at the edges of space and time, Planck's constant defines the limits of what can be known. The Planck length and Planck time, unimaginably small quantities, mark the boundaries where classical physics breaks down and quantum gravity takes over. At these scales, the universe reveals its granular texture, a cosmic fabric woven from quanta of space and time. The philosophical implications are equally profound. Planck's discovery forced humanity to reconsider the nature of reality. It suggested that the universe is not continuous but built from fundamental units, each governed by probabilities. The observer became part of the equation, measurement itself influenced outcome. This raised questions that reach beyond science, about free will, consciousness, and the limits of human knowledge. The quantum world is not chaotic, but it is unpredictable. It operates with a logic that transcends everyday experience, reminding humanity that certainty is not the essence of truth. The influence of quantum theory continues to grow in the 21st century. Today, scientists and engineers are building quantum computers, machines that harness the power of superposition and entanglement to perform calculations far beyond the capability of classical computers. These technologies are based entirely on the principles that trace back to Planck's quantization of energy. In quantum communication, entangled particles promise unbreakable encryption, creating a future of secure, instantaneous information transfer. Quantum sensors are being designed to detect gravitational waves, map the human brain, and explore distant planets, all guided by the same constant that Planck introduced over a century ago. The redefinition of scientific measurement itself reflects Planck's influence. In 2019, the kilogram, the fundamental unit of mass, was officially redefined based on Planck's constant, linking the very concept of weight to the quantum scale. This decision symbolized the completion of a journey that began in Planck's Berlin laboratory. The universe's smallest unit of action had become the standard by which humanity measures the physical world. Looking back, it is astonishing to realize that such a monumental shift began with a man trying to solve a single problem about the color of heated objects. Planck himself was a reluctant revolutionary, a physicist who believed in the harmony of nature and the beauty of existing laws. Yet his discovery disrupted those laws and gave birth to new ones. He once said, "I was led to the hypothesis of quanta by desperation, not by conviction." And yet, in that moment of desperation, he uncovered the framework that would sustain a century of progress. The story of Planck's theory is the story of human curiosity itself, the courage to question, the humility to admit uncertainty, and the brilliance to find order in the unknown. His work reminds us that even the smallest numbers can carry cosmic significance, that the universe's vastness is mirrored in its tiniest parts. Every flicker of light, every spark of electricity, every heartbeat of technology echoes with the rhythm of Planck's constant. In the grand narrative of science, Planck's discovery stands as one of the great turning points, a bridge between the old world of classical certainty and the new world of quantum wonder. It revealed that reality is not a fixed stage but a living, vibrating tapestry woven from quanta of energy. Through that revelation, humanity found not only new knowledge but a new sense of awe. The universe, once thought simple and mechanical, became mysterious, dynamic, and alive. And at the heart of it all lies a single symbol H, the constant that whispers the secret of creation, the measure of every quantum step the cosmos takes toward eternity.